on to part 4 of our space-time diagrams revisited. And so what we've done here is we've expanded our diagram from last time where we had Alice's plot, space-time diagram, her frame of reference, and then we figured out what Bob's space-time diagram, the axes, would look like if we put it also on the same plot as Alice's diagram. And this is what we got from last time. Note that, just to put some numbers here, we've chosen v equals 0.5 c for the relative velocity between the two frames of reference. Bob, in other words, is moving at velocity 0.5 c in the positive direction, which means gamma is 1.2. That will be important in a minute or two here. And we also mentioned last time that we had to be careful about the tick marks on the axes for Bob here. We can't just draw them in and assume they're in the same location because we have to go according to the Lorentz transformation equations. And we know that XA or XB and TB do not give us the same numbers in Alice's frame of reference, Bob to Alice or Alice to Bob here. So here's what we need to do. We need to say, okay, here's Bob's frame of reference in sort of standard form. And here are the points on his axes here. So for example, the point xb equals 0, tb equals 1 is this point right here. Okay, that's just on his tb axis. And this would be the point xb equals 0, t sub b equals 2, and so on and so forth. And the other points, this would be the point x sub b equals 1, t sub b equals 0, and so on and so forth. And so what we need to do is take each of the standard tick marks on Bob's frame of reference here in standard form and translate them, transform them using the Lorentz transformation equations onto the skewed axes here. We're not going to do all of them. We'll just do a couple examples so we can get the idea here, and then we're going to see what implications that has for how we can read things off the diagram. And in particular, we'll see that we'll be able to see time dilation and length contraction just from this diagram alone here, which of course makes sense because the whole thing really is based on the Lorentz transformation equation. So let's take a look at this. Bob's spacetime point, xb equals 0, tb equals 0. We're going to use the Lorentz transformation equations to figure out, we're going to be able to plot this point from Bob's frame of reference there onto Alice's plot here. And we expect it's going to appear on the t sub b axis, right? Because all these points are on the t sub b axis. In Bob's frame of reference, we showed that this is how the t sub b axis looks like when we put it on Alice's plot. And therefore, we know this point is going to be on here someplace. We just don't know exactly where. And that's what we need to figure out. So if we look at our equations up here, it's actually the top pair that work well this time. So we'll erase that and say, okay, because note I've got x sub b equals 0. So I can put 0 in for the x sub b's here. And t sub b equals 1. And so what I get for that, if I do that, so we're going to put these in here. So I get x sub a equals gamma. Now x sub b is simply 0 plus v times t sub b, which is 1. So I just get v times 1. And obviously 0 plus v is just v, so this becomes gamma v. And in fact, let's put some numbers in here for that. If gamma is 1.2 and v is 0.5 c here, 1.2, or really 0.5 c, and remember c is the speed of light, of course, and then we're using it in units of light years per year, so it just has the value 1 very nicely for us. So this becomes 0.5 times 1 and times 1.2, so 1/2 of 1.2 is 0.6. And this would be in units of light years or whatever we happen to, light type units we happen to be using there. So that gives us the x sub a coordinate of this point in Bob's reference frame, but transformed to Alice's. And then t sub a is simply going to be gamma times, now t sub b is 1 plus v over c squared times 0. In this case, x sub b is 0. And very simply, that just gives us gamma. And gamma is simply 1.2. Okay, so let's plot that now. So we say, okay, we found out that this point right here, that point there, from Bob's frame of reference, when I put it on Alice's plot, is going to appear at x sub a equals 0.6. So, this is 1, 2, 3, 4, so on. So it's about 0.6 is about right there. And t sub a is going to have a value of 1.2. So if we really move it up here, it's about right here is where it is. Now, when I'm putting tick marks on here, remember, tick marks need to be parallel to the appropriate axis. So all the tick marks here for t are appropriate to, or parallel to the x-axis, because really these represent many lines of simultaneity, right? These are all, this indicates, all along there is a line of simultaneity for t sub a equals 1, t sub a equals 2, t sub a equals 3, and so on and so forth. And they need to be parallel to the x sub a axis in this case. So tick marks on the time axis need to be parallel to the xb axis. So here's the xb axis. Tick mark location, according to our results there, is that. So I don't know if I've got that quite right, but something like that. We'll draw it big there. Okay? So that is, that point right there appears right there, sort of in that blob there. Let's do another one, though. We won't do too many of these. Let's do one more here for the t sub b axis. So let's change this, not t sub b equals 1, but t sub b equals 2. In other words, now we're looking at that point. Where does that point occur on this axis? Okay, or on Alice's plot, really. And so we come up here. We can just very easily change our equation. Xb is still 0, so the zeros still are there, but the 1 just becomes a 2 here, and this one over here becomes a 2 for our second case. And we see we get 2 gamma v, and of course it's not going to be 0.6 anymore, so we'll get rid of that for a minute. And down here we get 2 gamma, 2 times gamma plus 0, so we got 2 gamma times v, 2 times gamma, 2.4 times 1/2, essentially, gives us 1.2. And 2 gamma is simply 2.4. So now we have another point. In other words, the point xb equals 0, t sub b equals 2, on Bob's plot over there for his frame of reference, transformed onto Alice's frame of reference into the point, okay, x sub a equals 1.2. So here's 1.2 approximately, and t sub a equals 2.4. So if we sort of go up here, roughly speaking, it looks like it's someplace right around there. Okay, so that's that tick mark. Again, this tick mark is parallel to the x sub b axis because it marks out lines of simultaneity there, as we were talking about in the last video clip. And we could continue doing this. We could do t sub b equals 3 and so on and so forth. And you can see the pattern here. We got one there. Well, next one will probably be, well, will be something like this, roughly speaking, and so on and so forth. Okay? So that gives us the tick marks on the TB axis. And now let's do the x sub b axis here. So in this case, we're looking for, let's do this point right here. We're assuming, by the way, the origins coincide. So the 0 point here matches up with the 0 point there, of course. But this is xb equals 1. So now we're looking at the point x sub b equals 1, t sub b equals 0. Okay, because now we're on the x sub b axis here. So xb equals 1, t sub b equals 0. What are the x sub a and t sub a coordinates in analysis plot for that? And so again, we have a situation here where just plug in the numbers. So these are the things that are going to be changing here. And we'll see what we get. Okay, so x sub a, gamma times x sub b. So x sub b is 1 this time. So there's a 1 here. And t sub b is 0. So that's very nice. We'll just put a 0 in there. And for this one, t sub b is 0. And we get a 1 over here. So the top one is just gamma times 1 plus 0. So this just becomes gamma. And the bottom one becomes 0 plus v over c squared times 1. So it's gamma times v over c squared. And putting some numbers in here from before, gamma is 1.2. Gamma is 1.2. And c squared is going to be 1 for our units of light years per year. So I've got gamma times v, and that's going to be 0.6. 0.6. So now we have this point right here, is what we're working on now, and that one's going to come over here in Alice's coordinates to xa equals 1.2, so about right there, and t sub a equals 0.6. So up here like this, about right there. I'm a little off in my plot here. But so that's the location, and the tick mark now is going to be parallel to the TB axis. So it's, again, roughly speaking, you want to draw something like that. Maybe a little off there. Try not to make it too big, but that's what that tick mark looks like. Okay, let's do one more here. So xb equals 2, because then we'll see the pattern. xb equals 2. So now we're looking at this point right here on the x sub b axis. T sub b is 0. And so we come up here. The zeros stay the same. This becomes a 2. This becomes a 2. And we get 2 gamma and 2 gamma v over c squared in those cases. So we get 2.4 and 1.2. 2.4, 1.2. And so we go x sub a equals 2.4. So over to about right here. And 1.2, so we're about right there. And we try to draw it roughly parallel to that. And then we get other results as we move along. So the next one would be something like about right here probably, and so on and so forth. Okay. Now, what that means here is there are lines of simultaneity and lines of same location in terms of Bob's axes here. And so again, they're parallel to the t sub b axis, so they would be roughly like that, like that, like that. Okay, and extending down too, of course. All the way down there. Okay? And then the line, so those are lines of same location. Hope I said that right. Lines of same location here for a given value of x sub b. So this is 3. This is 3 light years on the x sub b axis right there. And anywhere on this line here, as far as Bob concerned, those would be events that happen at 3 light years for any given time. And then the lines of simultaneity for Bob on this plot are parallel to the x sub b axis. So it sort of looks like this. Try to get it in here. And of course, it goes the other direction too. Okay, hopefully you get the idea there. This is really something you need graph paper for to get it looking right. Okay, so now let's see what we can get out of this result here. Let's look at a case where we have a certain point, a certain space-time event. And let's focus on Alice's coordinates here for a minute. And let's do her a few lines of simultaneity in same location. So lines of simultaneity here, sort of there, like that. I don't want to make it too messed up here. Something like that. So I can see it's getting a little messy there. But let's see if we can see what's going on here. So what this means is anywhere along this more or less black straight line here, that's a line of simultaneity for Alice. That's t sub a equals 1. Okay? So let's see where that intersects with Bob's t sub b axis, in particular right here. Right there. If that space-time event occurred, a flash of light say, Alice would measure it at t sub a equals 1. Okay? Right there. And her x sub a would be maybe 0.4 or something like that down here. Okay, so that would be, for Alice, it would be x sub a equals 0.4, t sub a equals 1. Okay, that would be the flash of light, and her coordinates for the flash of light. Look at what Bob's coordinates are for the flash of light. Okay, so let's figure that out. So for this flash of light for Bob, clearly it's happening on his time axis, so that's x sub b equals 0 for him. Okay, it's happening right where he is, so it'd be xb equals 0, okay? Because the t sub b axis is, by definition, x sub b equals 0, his location. And what's the time for him? The time for him is, well, note where the t sub b equals 1 point is. It's right here. It's right there. And that's less, the flashlight is occurring less than that time. It looks like, from here to here is 1 for one light, not 1 light year, 1 year for Bob, from there to there, tick mark of 1. And therefore, maybe it looks like about 0.7, just roughly speaking, maybe 0.75, someplace in that region. So we'd say TA, just very roughly here, we're trying to get a rough idea, 0.7, 0.8, someplace in that vicinity, just trying to read it off our somewhat imprecise graph there. But it's precise enough to see that clearly when Alice measures that event at 1 year on her clock, here's synchronized clocks, Bob, his clock reads 0.7. Oops, sorry, this is not A here, B. Bob's clock is 0.7. What do we have there? That's time dilation. Alice sees Bob's clock running slowly, then more slowly than her clock. Okay? So, and we could do a precise, obviously, it's going to be a 1.2 factor here, we know from earlier results. And so I don't know if, 1 divided by 1.2, it's probably not quite 0.7, but it's in the vicinity there. So that's time dilation that we can see out here as well. And it's a little harder to see on this plot, but you can also see length contraction, okay, because a given length is going to be shorter to Alice than to Bob. So let's see if we can just get a feel for that. You see that a given length is going to be shorter for Alice compared to Bob. The proper length in Bob's frame of reference, say for his spaceship. So let's look at this and see that, well, what is length here? Let's say just this distance here, right there, is a standard length of 1 to Alice, right? Okay. A standard length of 1 to Bob is this vertical line here on this plot. Okay. Clearly, this line is longer than that line. Okay. So in other words, if Alice is comparing 2 points, say the beginning and end of Bob's spaceship, she'll get a shorter value, a shorter measure of that than Bob will. And it's a little messy there, not quite so precise, but hopefully you get the idea that this actually shows not only time dilation, it shows length contraction as well. And in fact, one other thing you can see here, and we'll do this in the next video clip, is you can see the relativity of simultaneity and leading clocks lags. That's what we'll work on next.